Hello teachers, let's wrap up our chapter 14 and talk about dilations. A dilation and its construction is something you're going to understand at the end of this section, and applications of dilation. So what is a dilation? Isometries preserve distance, so an image under isometry is congruent to the original image. Remember, we talked about that in previous sections. So an isometry preserves congruence, so angle length, segment length. Okay. A different type of transformation is created when a slide is projected on a screen. The objects on the screen are enlarged from their original size on the screen by the same factor. And this is an example of a dilation. So you see, you have a projector here and you have your image. Your image is congruent to your original image that's in the projector, except this is maybe by a factor of 20. So there's always going to be a scale factor when you have a dilation. So here we go. We have a dilation here. Each side of triangle A primed, B primed, C primed, which has had a dilation applied to it, is twice as long as the corresponding sides of triangle ABC. Okay, now here's what I want you to notice. When you have a dilation, you're going to have from a point or a center O, okay, and you're going to connect your vertices. If you have a polygon, the vertices of your polygon are certain points, okay, with a ray that goes from the center O to your vertex A, and then your vertex A primed by a scale factor. Okay, so you're going to find this distance here, okay, and then you're going to have a scale factor here. Now the scale factor for this particular dilation is 2. So this is twice as big. This triangle, all the lengths are twice the size. The angles remain the same. Okay, so the angles are congruent, but the lengths are twice the size. How do you do that? Again, there's that ray or that line that we talked about, okay, that connects your center O to your vertex and then continues on to the A primed, which is your dilation point for A. If it's twice as long, then you would have twice your length from 0 to A. Okay, so then you just double it and then go to A primed. And same thing with C. So notice first you measure the distance from 0 to C, and if it's twice the dilation, then you need 2 of these. So you keep going, and there's your C primed. Again, you measure from 0 to B, and since the scale factor is 2, then you need twice these, 2 of these, so here and then another one to get to B primed. And that creates your new triangle. Again, it's going to be congruent as far as the angles are concerned, but it is a similar triangle with all the lengths twice as long as the original lengths. A dilation from the plane to the plane with center 0 and scale factor R, where R is greater than 0, is a transformation that assigns to each point A in the plane the point A primed, such that 0, A, and A primed are all collinear. Remember, we noted that in the last picture. 0 is not between A and A primed, and 0, A primed is equal to the scale factor R times the length of OA. 0 is its own image. So again, we go back. That is really looking at this. So again, you have these points that are collinear, 0, A, or O, A, and A primed, where the length from O to A primed is the scale factor R times the length from O to A. Okay? It is possible to define a dilation when the scale factor is negative in the same way as in the preceding definition for positive scale factor, except that O must be between A and A prime. And I have some images for you to help you think about this. Okay, so first look at the top left image. We have a scale factor of 2. Okay, so let's look at this one. And this is just like the problem we just looked at. So here is your point O. Notice again, O, A, and A primed are collinear. They all lie on the same line. And the distance from O to A primed is twice the distance then from O to A. And the distance from O to B primed is twice the distance as from O to B, and then the distance from O to C primed, you get the point, is twice the distance that it is from O to C. That's what happens when you have a scale factor of 2. Well, what if you have a fractional scale factor? So they have 0.5. We might look at it as 1/2. Of course, they are the same thing. Okay, now your pre-image or your original image is the one in red. I want you to notice that. Red is your original image, and then your dilation is in the beige color here. So if you have a proper fraction or a decimal between 0 and 1 as your scale factor, what's going to happen? So notice the distance between 0 and A, remember to the original image, is cut in half now. So your dilation is smaller, and it lands between 0 and A. See, A primed, B primed, and C primed are between 0 and A, again, because you have a scale factor of a fraction or a proper fraction. Okay? Well, what if you have a negative scale factor? Well, notice what happens is that ends up giving you a reflection. Okay, now not a lot of negatives showed up in this section, so don't stress over the negative. I just wanted you to have a visual for it. So again, you have the dilation. It's negative 1.5 or negative 3/2 is your R value if you want to look at that. Okay, so again, A and A primed and O are collinear. They lie on the same line. So the distance from O to A here is like, we just call that 1. And so this is a scale factor of 3/2. We multiply this 1 times negative 3/2, and it shoots it back this direction. Okay, again, from O to B, that's a scale factor of 1. So negative O to B is going to go backwards, okay, to negative 3/2 in that direction. And then a scale factor from 0 to C is considered 1. And then we go the opposite direction along the same lines, collinear. Okay, we're just going backwards. That's what the negative is. And that distance is going to be 1.5 times this way. Okay, and then if you have a negative 1/2 as your scale factor, then you would have an image like this. Okay, we're going to focus mainly on these two. Again, I just wanted you to have an idea of what a negative scale factor would do to your dilation. Now here we go. We've got find the image of the quadrilateral ABCD under a dilation with center 0 and scale factor 2/3. So here we go again. We have an R value 2/3, a proper fraction, right, between 0 and 1. Therefore, our blue image is our dilation. Our image got smaller, right? So how do you handle this? Again, the first thing you do if you wanted to construct this is draw a line with your straight edge from 0 to the original image B, right here, because your blue image is not here yet, from 0 to B. And then you would measure 2/3 of the distance on that line, and that is where your B prime comes. Okay? And then you would draw, again, straight edge from 0 to C, and then measure 2/3 of that line segment length, and that gives you C primed. You draw a line segment from 0 to A. I guess I could have done that first. It's kind of hidden back there, from 0 to A, and then you measure 2/3 of that distance, and that gives you A primed. And then you measure from 0 to D, again to the original image, and then your scale factor is 2/3, so you measure 2/3 of that length, and that gives you D prime. And then you just connect the points, and that's going to give you a similar quadrilateral, okay, the same angles, congruent angles, but side lengths with a scale of 2/3. Now, dilation with center 0, O, I keep saying 0, I apologize. The dilation with center O and scale factor of R, where R is greater than 0, so we're keeping it positive right now, has the following properties. First of all, the image of a line segment is a line segment parallel to the original segment and R times as long. Okay, so let's go back and look at our image, our previous images, and make sure that makes sense. If we look at the problem that we just did before, okay, so for instance, let's check out line segment BC. Okay, so here's the original line segment BC. Well, the dilation B primed, C primed, notice those are parallel lines, and B primed, C primed is 2/3 as long as BC. And that is true for all 4 of those line segments. So if you take a look at line segment CD, okay, then we can compare that to its parallel C prime, D prime. They are parallel, all right, and not only that, the line segment C prime, D prime is 2/3 as long as CD. And again, that's true for line segment AB compared to A prime, B primed, and AD compared to A primed, D primed. Okay, so you get parallel line segments when they go through a dilation, and they are R as long as the original one. Now, that is as long as, remember, R is greater than 0. If R were less than 0, remember, you don't get parallel line segments anymore because you have a reflection. All right. Second, the image of an angle is an angle congruent to the original angle. So this is making it official, okay? And I mentioned that a couple of times for you already. So if we go back and look at the image that we just had a dilation with a scale factor of 2/3. So notice the angles are all the same. So right here, if I take a look at angle ABC, and then I take a look at angle A primed, B primed, C primed, these are congruent angles, okay? Or the angle BCD over here is congruent to angle B primed, C primed, D primed. Okay, so let's do an example. We're supposed to show that triangle ABC, notice that is the larger triangle, is the image of ADE under a dilation. They want us to identify the center of the dilation and the scale factor. So remember, the center of the dilation is like the O value that you're projecting from, okay? So whenever you have a figure embedded in another figure, where they line up in the corner is a great place to center it. If that's the way that it's lined up, you'll have some homework problems that you will want to do that. So it'll ask you what transformation and dilation will give you the other figure. If you can line, if you have congruent figures, first of all, that's important, and you can line one of them up inside the other one, then you can let A be your center. So point A, or you could say it's the point 1, 1, right? And the coordinate axis is your center. Now let's figure out this scale. So let's think about this. We have the original is the ABC. No, that's the image, I'm sorry, of ADE. So the original is this guy right here, ADE. So would you say that R is bigger than 1, or is R less than 1? Well, if your image got larger, and ours did, then we know that our R is definitely greater than 1. If your image gets smaller, then it's less than 1. And that's why you want to read your problem very clearly. ABC is the image. Okay, that's after dilation, so ADE is the original. Now, what is our R value? We need to figure that out. So you can look at this like proportional. So if you look at side length AE, okay, now, by the way, you always want to put the image value in the numerator and your pre-image or your original in the denominator. So if I look at my image value AC, if we compare AC, that's going to compare to AE. Does that make sense? It's like it's dealing with similar triangles. So AC compares to AE. AC is how long? Well, let's count. So we're starting at 1 and it goes up to 7. So that's 6 units long, or you just count them 1, 2, 3, 4, 5, 6. So that's 6 units long. So my AC is 6. And my AE value, 1, 2, 3 units long. And that gives us 2. So our R value is equal to 2. Now, I highly suggest checking other proportions or ratios as well. Okay, so if I looked instead at AB, which is my image, working on the left side now, compared to AD, my original. AB is how long? From 1 to 5, so it's 4. And AD goes from 1 to 3, that's 2. And notice that also gives us 2. So if you have the option, I would definitely check at least 2 of those measurements just to make sure you were doing it correctly. Now let's rehash this information a little bit. Again, AB compared to AD is the same as AC compared to AE, and we got 2. Okay? And we choose 1, 1 as the center of the dilation and 2 as the scale factor. So again, 1, 1 is that corner where the 2 fit together, okay? And then we just scale from there, okay? From our center, A, or 1, 1. How about applications of dilations? One way to make an object appear three-dimensional is to use a perspective drawing. If you've ever taken any drawing courses, you've done this before. So for example, to make a letter appear three-dimensional, we can use a size transformation with an appropriate center, O, and a scale factor with selected images to create a three-dimensional effect for the letter C. So you'll see here, so notice our scale factor, O, and then here's our original image for a C, and then you project it to make it larger, and notice the shading in blue makes it look three-dimensional, like a super thick C. And so this is something that is used in art all the time. Now we have another problem. Show that triangle ABC is the image of triangle APQ under a succession of isometries with a size transformation. So basically, we want to do, you remember what the isometries are that we know? You could do a transformation, and that's when you move left, right, up, down, or a combination of those, okay? You could have a reflection. I'm not doing these in any particular order. You could also have a glide reflection, which really is a transformation and then a reflection. What am I leaving out? A rotation. All those are isometries. Now remember, what's important about an isometry is you get congruent figures. But now when we throw in this extra thing called a dilation, you get similar figures, but not congruent figures necessarily. Okay? Now they want us to do this. So we have triangle ABC. I got to find that. It's the image. So the blue one, ABC, is our image. Okay, that's our outcome. Triangle APQ, I'm going to highlight over here maybe in pink. This is where we're starting in pink. So APQ, that's our original image. Now we want to do something to this to turn this into image ABC. Okay, what are the things that we could do? Remember how I gave you a hint in the last problem? If you've got congruent images and you're trying to turn one into the other one, a nice way to handle that is if you could do a transformation to get this image inside your pre-image inside your original image. And in this picture, it's already done for us. That is what A, P primed, Q primed is. Now, what did we do to get pink highlighted APQ into position of A primed, P primed, Q primed? What could we do to get there? Well, it looks like we could do a rotation, right? Couldn't we just rotate? Would that be like a half angle if we just rotate 180 degrees? Do you see that? So if I just take Q and I rotate right up here 180 degrees, then Q would land on Q primed, P would land on P primed, and A would be right there in the corner like we want it. Sure, that's it. So here we go. Transform APQ by a half turn in A to obtain AP primed, Q primed. Okay, they didn't rename A as A primed. Sometimes they do, sometimes they don't. Now, a half turn, that's 180 degrees, right? So that anytime you see half turn, that's always what that means. Now we can do our dilation. So now we've got our reddish purple triangle on the inside, and we're trying to create the image and make it larger, right? So we know our R is greater than 0 because our image is larger than our pre-image by a scale of what? Okay, so let's compare. We've got line segment AC. Remember, you always do your image over your original. That would be AQ primed. So what's the length of AC? Well, let's say 1, 2, 3, 4, 5, 6 units. Over AQ is 3 units. So we have a scale factor, once again, of R is equal to 2. But don't let that convince you. Go ahead and check the other one too. So we could say AB. We could take a look at AB over AP primed. Length of AB, 1, 2, 3, 4 over AP primed is 2 units long. Again, we get a scale factor of 2. Okay, so how would we write this up? We say C is the image of Q primed under a dilation with center at A and a scale factor of 2. So B is the image of P primed and A is the image of itself under this transformation. So A, we just kept A. Okay, and make pretty good sense? Okay. All right, and then one more conclusion. It says, therefore, triangle ABC can be attained from triangle APQ by first finding the image of triangle APQ under a half turn. Remember, we did a half turn in A, and then applying a size transformation with center A and scale factor 2 to the image. Just restating everything that we did. Okay, two figures are similar. Remember, if and only if it is possible to transform one onto the other by an isometry or a sequence of isometries followed by a dilation. All right, so we could say, instead of proving similarity like we did before, you can prove that one figure is similar to another figure if you can perform an isometry, which, remember, we could list those again. It's a transformation, a rotation, a reflection, or a glide reflection. And it doesn't have to be just one thing. It can be a combination of those things. And then followed by a dilation to make it either bigger or smaller. Okay, I have a homework example for you. And then another one, and then we will be finished. In the given figures, describe a sequence of isometries followed by a dilation so that the larger triangle is the final image of the smaller triangle. Okay, so we want the larger one to be an isometry and a dilation to produced from the smaller one. I had to think about how I started that sentence. So what could we do? Right? Well, remember, the first thing we did last time we had a problem like this is we did some kind of transformation where we moved the smaller one, the original. So again, this guy right here is what we call the pre-image. Okay, so if we could slide this inside our triangle, and let's look at it. Notice it's 2 units wide at the base, so I'm going to move it 2 units wide, and then it's 1, 2, 3, 4, 5, 6, 7 units long. I feel like I could have made this bigger and it would be easier to take a look at. All right. Now that's where we need to get started with our dilation, but let's write down what in the world we did. What did we do? So we slid our black pre-image triangle down, right? Down how many units? I would say down. I even counted it, but I'm not positive. So I'm starting at the bottom here. That's 1, 2, 3, 4, 5, 6, 7. We moved down 7 units. Notice we didn't have to move it left or right, but that is a possibility, okay? Down 7 units. Now let's determine our scale factor. We know that it's greater than 1, right? How do I know it's greater than 1? Because my image got bigger instead of smaller. So if you want to make your image smaller, then your scale factor is between 0 and 1. If you want to make your image larger, your scale factor is bigger than 1. And so it definitely got larger. But how much larger? So what I'm going to do is I'm going to measure my side lengths, and I'm going to do it a couple of times just to be certain. So if I count my green, that's 1, 2, 3, 4, 5, 6, 7. That's like the third time I've counted that, right? Remember, the original image goes in the denominator. Okay, so I have that length of 7. And the numerator is my blue triangle. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It appears to be 14. I promise you all the R's are not 2. Now, just to be confident, and that wasn't the easiest one to check, maybe I should check another direction as well. So, you know, my base here, or my horizontal part of my triangle there, that is 2 units across. Remember, that goes in the denominator. And in the numerator is your image. And that's 1, 2, 3, 4 across. Definitely 2. So our R is equal to 2. Okay, so we moved down 7 units. That was a transformation. And then our dilation is R equals 2. And then we could say, if we had a name for that corner, we could say that our center for the dilation is whatever that value is. Okay, so the top right corner. So the center is the top right corner. It would help if some of these points were named, but they weren't in the homework, so I'm showing you just as it is. So the top right corner is your center of your dilation. Okay, now let's try another homework example. We're just going to call this done. All right, the figure describes a dilation with center O and image in bold. Okay, find the scale factor and the lengths designated by X and Y. Okay, so notice I'm going to highlight it. I know it's bold, but that is our image. Okay, which means this guy over here is our pre-image. Okay, now they want to know the scale factor, so let's start there. How can we find the scale factor? Well, you need a value from your image and your pre-image, and it has to be corresponding measurements. And so I see I have a 24 for my line segment of my image, and I have an 8 for my pre-image. So I'm going to say 24 over 8. Okay, so that simplifies to 3. So that is my R value. Now, I suggested that we always check with another measurement, but now when I start checking with my other measurements here, okay, I don't have any other measurements. So, you know, when I compare, I'm comparing this side to this side, or if I look at this side, it would have to be this whole side compared to this side. So, so I would have to have 20 plus Y compared to the original Y. Or if you look at this measurement, the full image is X plus 12 compared to the pre-image of X. So I don't have enough information anywhere else to calculate another comparison to figure out my R is 3. So I'm going to be confident that my R equals 3 is right. We don't have to check it. We just do to make ourselves feel better. But now I'm supposed to solve for X and Y. But you know what? I have what I need to solve for X and Y. Okay, so check this out. Some algebra. So my R, or my ratio, or my scale factor is 3. That's got to be the scale factor for this whole length compared to the original Y value here. So I just need to solve this equation. So remember, this is 3 over 1. Or you could even use 24 over 8 if you like that. But I like the reduced one. It's easier math. You cross multiply when you're trying to solve a proportion. So 3Y is equal to 20 plus Y times 1, which is 20 plus Y. I'm going to solve for Y, so I need to subtract Y on both sides of my equation. Why am I doing that? Because I have a addition property of equality that says whatever I do to one side, I can do to the other. Equals 20, so that means Y is equal to 10. So now I found the scale factor, I found my Y value, and in green, let's find our X value. So once again, this proportion of the image over the original is equal to 3 over 1, which is our scale factor. So I cross multiply this way. 1 times X plus 12 is X plus 12. I cross multiply this way. That gives me 3X. To solve for X, I need all my X's on one side. I'm going to keep it simple and subtract X from both sides of the equation. 3X minus 1X is 2X. I divide both sides by 2 to get X is equal to 6. Okay, so if Y is 10, X is 6, and Y is 10, then you will see all of those ratios will be 3. So that's 30 over 10. This one is what, 18 over 6, and you still have 24 over 8. Okay, if you have any questions about the homework, please let me know. I hope you have a great day.